exponents. So hopefully you feel pretty confident about that information. But let's look at we're going to start with the exponent worksheet. So if you want to find that slide, we'll start with the exponents. I apologize, this picture didn't come out as neat as I wanted it. The next one, I took it in my kitchen instead of my office, which has better lighting. So the first two problems here, the goal was to see how a negative in front of the base can change the graph. So in number 1, we have 2 to the positive x, and number 2, we have negative 2 to the positive x. And you can see that this is a reflection over the x-axis. So remember, when the y value is negative, which is really what that base ends up giving me my y value. When I have a negative y value, it makes all the y's negative, reflecting it over the x-axis. So then looking at 3 and 4, the base was all the same here. So the goal is for you to kind of understand how a negative can change the graph based off of the location of that negative. So if we look at 3, now the x is negative. And when the exponent is negative, or the x, that makes us have a decreasing function. It also, kind of looking at the two of them together, you can see it's reflecting over the y-axis. So if the base is negative, it reflects over the x-axis. When the exponent is negative, it reflects over the y-axis. And then number 4 was doing a combination of all of that. There were 2 reflections here because the base, the negative 2, so it's making the y values negative. But then the exponent is also negative, so that's also making the x values negative. So this is a reflection over both x and the y-axis. So the goal of the first 4 problems here was kind of just looking at that, sorry, screen flip there, looking at the negative and kind of understanding how a negative affects the exponent, the graph of the exponential function. So the base is changing the y, but the exponent is changing the x values. Does anybody have questions on those 4 problems? All 4 of them have the same horizontal asymptote at y equals 0. So the horizontal asymptote is not changing, it's just at y equals 0 in all 4 of these graphs because the graph is not shifting. So there's really no shift to the graph vertically or horizontally, it's just reflecting. So then the other 4 graphs, this picture came out a little better. These graphs did have some shifting to the graph. So if we're looking at number 5 and 6, the -4 and the +1 affects the horizontal asymptote. And it affects it because that's shifting the graph vertically. And that's where our asymptote lies, because it's kind of moving a vertical up or down, even though it's a horizontal asymptote. Because it's in y equals form, it's that vertical shift, kind of the horizontal line shifting up or down. So this graph is shifting down 4, which corresponds directly with that horizontal asymptote. Number 6 is shifting up 1, and again, that corresponds directly with our horizontal asymptote. So all exponential functions have horizontal asymptotes. If it's not shifting up or down, then it's just at y equals 0. So the extra value, that k value, the -4, the +1, is the part that makes the graph shift up or down. And that also then corresponds directly with the horizontal asymptote. And notice number 5 crosses both x and y axis, and that's because it's shifting below the x axis. So because it's moving down, it's going to cross both x and y. The last 2 graphs, so try that again. When the exponent has a value added or subtracted, remember that is our h value. So these are still in that form, ax minus h plus k. And that was the form that we talked about in chapter P and chapter 1. And then also with the parabolas that we graphed in chapter 2. So this graph, that x minus 2 is really shifting right to. And you can kind of see that in the graph. It also is reflecting down. So because the base is negative, so it shifts right to, and then it reflects down. And then number 8 is the same graph, except it doesn't have that reflection going down. So it's a base of +2, but it's still shifting to the right. So the only difference with 8 and 9, you can see, is the y values. So the y values, I'm sorry, in 7 and 8, the y values are negative in 7 because the base is negative. So does anybody have questions on the exponential functions? Please ask if you do. Okay. So if you want to find the logarithmic functions, we did number 4 together. And here are the pictures, the graphs of the others. I also have my work shown below so that you can kind of see how you're applying the properties of those 3 logarithmic function or logarithmic properties. And the log functions have a vertical asymptote. So in number 1, the vertical asymptote is at x equals 0. In number 2, it's still at x equals 0. And that's because your vertical asymptote is in x equals form. So it's going to change when there is a quantity attached with x, because once there's something with x, it affects x. So that's going to affect the vertical asymptote. So in 3, we did 4 together yesterday. This graph is shifting left 2 units. And that changes the vertical asymptote because it makes it shift left 2 units as well. So it would be the asymptote at x equals -2. So I'm going to go through number 5. I thought it was a good one to kind of talk about, just to get you to think about how to graph these and that thought process to try and use the properties. But like my work down here would be the work that it corresponds with the properties of the exponents or log functions. So those 3 properties that we talked about. So I'm going to go up to number 5. And we're going to try and use these properties again. So log base A of 1 is 0. Log base A of A is 1. And then log base A to the x is equal to x. So we're going to try and use these properties to help us find some values for x. So remember, when you're picking values for x, you're picking the numbers that are next to the log. The value on the other side is our output, and that is our y. So looking at the expression here, we have the log base 3, and then in the middle of the parentheses is 1 minus x. So log base 3 of 1 minus x. So I want my first x value to be 1. So my goal is to get it to be 1 here. But inside the parentheses, we have 1 minus x. So I need to choose an x value that when I take 1 minus x, it's equal to 1. So really, I need that 1 minus x to equal the value of 1. And the reason I need that to happen is so that it applies to that first property. So Joe, can you give me a number for x that when I take 1 minus that value, it equals a positive 1?
0.
So Joe said 0. 1 minus 0 is a positive 1. So that means I have the log base 3 of 1 minus 0, which is really the log base 3 of 1, which is equal to 0 from property number 1. So property number 1, we're going to have an ordered pair at 0, 0. So our second property, I want the base and the value next to the log to be the same. Well, my base is 3. So that means I need the expression 1 minus x to equal 3. Because my base is 3, so I want this whole thing to become 3 as well. So Gianna, if I have 1 minus x, what value could I have for x that makes that number 3?
Would it be -2?
Yeah, perfect, -2. So then just showing you how that works. I would have 1 minus a -2, which we know is the log base 3 of 3, and that equals 1. So my second ordered pair would be at 2 and at 1. And now the third one is when I need to start applying those exponent properties. So I would want my number to be 3 squared, or I would want my number to be 3 to the -1. So I need to think about 1 minus x becoming 3 squared, or 1 minus x becoming 3 to the -1. So Peter, what number could I choose so that I end up with 3 squared, or 9?
You could choose -8.
Yeah, and then for the next one, Peter, if I want 1/3, 1 minus what makes 1/3?
2/3.
So those would be the x values, so that when I apply them into my equation, 1 minus -8 is really the log base 3 of 9. Well, 9 is 3 squared. The exponent is what my property would evaluate to. So whatever the exponent is what it's equal to. And then the last one, Peter said, was 2/3. 1 minus 2/3 is really the log base 3 of 1/3. Well, 1/3 is 3 to the -1. So then that evaluates or breaks down to just -1. So these would be the ordered pairs that I would be graphing. Any questions on those last two? It might be helpful for you to take that expression in the parentheses and say 1 minus x is equal to what number? What's my goal? Because then the number I'm choosing for x, you can see, is in my T chart here. There we go. So I'm picking those numbers for x so that it corresponds with it. Hannah, question?
Yeah, so instead of doing 3 to the -1, could I also have done like 3 to the cubed?
Sure, you could definitely do 3 cubed. It's just 3 cubed is pretty big. 27 is a larger number to work with for your x, like you'd have a large x value. Sometimes choosing the negative exponent helps you see where the curve appears in the graph, but you could definitely do 3 cubed.
Okay, thank you.
Yep. So if we graph this, making a little graph. And then just plotting the points, we have a point at 0, 0. We have a point at -2 and 1, at -8 and 2, and then at 2/3 and -1. So my graph is going to continue on the left side. It's going to continue to go up. And if you, as Hannah said, she chose, she tried to use 3 cubed. So she would have had another point further on that left side that would again continue to approach the vertical upward positive infinity values. And then that, using that exponent of -1, so the x value of 2/3, that kind of shows you where it's going to start to curve. So that graph starts to curve at that location. And then I have a vertical asymptote. My graph kind of went through my vertical asymptote. It shouldn't have, but I'm going to have a vertical asymptote at the value of 1. And that is because of that 2/3. So that fractional value, if I had 3 to the -2 or 3 to the -3, it's going to just continue to approach the asymptote. Any questions? Okay. So as I said, today we're going to talk about properties, more properties. So these are 3 properties of logs, but we're going to talk about properties of like simplifying. So expanding them or condensing them together if I have multiple logs. So these properties here are just with one logarithm. we're going to look at now having 2 logarithms or 3 logarithms, just like I could have exponents. So I could have a squared times a cubed times a to the 4th, and I would want to combine all those together. So we're going to look at those properties. Are there questions on graphing? So tomorrow we will review the first 3 sections. So we'll review graphing again tomorrow and the concepts in the first 3 sections. So if you look at page 13, slide 13, just a short little page of notes here. It really is just like, I think, 5 examples that we're going to look at. This is a review of, as I said, the properties of logarithms, dealing with having multiple logarithms. And the first property we have is called the change of base formula. The change of base formula helps us evaluate logs that we cannot evaluate using exponential form, but it helps us evaluate them using the calculator. So this change of base, if you look at the form that's in the box, this is what the calculator has embedded in its program. So the wonderful thing about calculators is that when you press a button in the calculator, it already has a program in it. It has code, that would be the word, to calculate this log base a of x. But what it's really doing is it's taking the log base b of x divided by the log base b of a. And that base b is generally the value of 10 because that's the like common logarithm. So if you see the first example, I think it seems a little confusing, but I think you'll remember, oh, this really isn't that confusing. It says use the change of base formula to evaluate to 3 decimal places. Does anybody remember in your calculator where you can find the log button in your calculator? So look at your calculator. There is a place to evaluate logs. So that's what this question is asking us to do. Usually when we have the calculator, I'll pull mine up for you. So usually we use just the log button on the left of 7 or the ln button on the left of 4. Those are the 2 log functions that are just on that direct calculator screen. But if you hit the math button and you go down to A, you see it says log base. That's the change of base formula in your calculator. So again, that's underneath math. Math is found right underneath the alpha button on the left side. And then you're going down to the letter A. You might have more options than I have in your calculator. So you might have to scroll down a little further to get to A. When you hit enter, my calculator now has the form of a logarithm. So the base was 4 in the example. So log base 4 of 30. So I would have log base 4 of 30. And then you hit enter and it said 3 decimal places and I have 2.453. What the calculator is really doing, just so you understand how the calculator is working, it's really taking the log of 30 divided by the log of 4. That's the change of base formula. So that's what's in the calculator already. The base here is really a little 10. That is called the common log. And that's the one that usually is just embedded in your calculator next to the number 7. Does anybody not have the log or the change of base formula in your calculator? Or can anybody not find it? Joe, question.
I was just saying my calculator doesn't have that.
Okay, so Joe, if it doesn't have it, what you're going to do is you're going to hit the log function, the log button on the left next to 7, and then you're going to type in 30. You're going to hit the divided by sign, and then you're going to do the log and type in 4, because that's really what the calculator is doing if you had that button. So the log of
Okay,
the
thank
base
you.
number divided by the log of the base. You're welcome. I'm sure you're not the only one that doesn't have it. So you can see I get the same answer. So it's actually good to show you how the calculator really is calculating it using this formula. So it's the log of the number divided by the log of the base. And it's called the change of base formula. So 2.453. Anybody else have questions on that? So that is a way for us to evaluate logarithms that aren't able to be solved using exponential form. So any logarithm we can evaluate. We try and use exponents to give us exact values, but sometimes it's not going to be exact. So then the three properties underneath, so we had three properties that we were just looking at for graphs. These properties apply to having multiple logarithms. So not just one logarithm, but we have two logarithms or three logarithms, or maybe even four, depending on how big our expression is. So these are for expanding and condensing logarithms, depending on what we're trying to do with the problem. Our end goal is going to be to solve these equations for log and exponent form. So that's why we have these properties to help us. The first one we have is the log base A of u times v. This is called the product property. I can separate that into individual logarithms by having the log base A of u plus the log base A of v. This one is very similar to the exponential property that we talked about in section 3.1, where I would add my exponents together. So if you're multiplying and you have the same base, I can add the logs together, but in logarithm form, it actually creates two separate logs. The second property says the log of A, log base A of u divided by v can really be expressed as the log of base A of u minus the log base A of v. Again, this goes with the division property. So if I had a to the x divided by a to the y, then I'm subtracting. So that's the division or the quotient property. And you see it works the same way with the natural log versus the log of a base. And then the last one we have is the log base A of u to the exponent of n. That exponent of n actually pops in front and becomes multiplication. So this becomes n times the log base A of u. So the exponent can be moved into multiplication form. And this is similar to the power to a power property where you end up multiplying those two together. So we're multiplying the log with the exponent. So in the example below, it says use the properties of logarithms to verify that negative natural log of 1/2 is really the natural log of 2. So verify means take the one on the left and show how it can become the natural log of 2. And it wants us to try and use the properties above. So how could I try and use the properties to show that the negative natural log of 1/2 is really the natural log of 2? So think about those three properties above.
Would you move the -1 to be an exponent?
Excellent, yeah. So really this is -1 times the natural log of 1/2. So Peter is saying take that number in front and move it as an exponent. So we have the natural log of 1/2 and then to the -1. Peter, if you have a -1 exponent, what is that really doing with the 1/2?
It's gonna flip it.
Yeah, it's going to flip it. So that's just using that third property. So when I have a number that's being multiplied in front of a log or a natural log, we can move that number into the exponential form. And then if you have 1/2 to the -1, that really just flips that fraction and makes it a +2. So verifying is just applying a property to show that I can make the left side equal to the right. Any questions on that example? The next two examples ask us to expand. So this is trying to use, again, those properties of logs to try and expand the problem. So right now we have a 1 log. We want to try and break it up, and it says write it as a sum, difference, or constant multiple of logarithms. So our goal is to try and break this apart and expand it. The reason we want to do this is because eventually we're going to try and solve equations with logs and exponents. And that might be a process to help us to get to that solving equation part. So if we try and look above, Darby, we have the log base 10 of 5x cubed y. How do you think we could try and start expanding this, Darby, based off of the information above?
Would you use the first property to try and expand it?
Yeah, excellent. So we're going to use that first property. Darby, how many logarithms would we be creating?
We'd be creating 3 because there's 3 different ones.
Excellent. So there's 3 values being multiplied together. So we would have the log base 10 of 5. The x is separate. And then the y is again separate. So there's the constant value of 5, and then there's an x cubed and the y. Darby, what else would you do then? Is there anything else we can do to simplify this?
You can solve for log base 10 of 5.
We could do that, yes. You are awesome that you're thinking that. Is there any way to continue to expand it though, or rewrite it?
Could you expand it since it's x to the 3rd?
There you go. That's what I was thinking of, yeah. How would you work with that x to the 3rd? Where would that go?
You put the 3 in front of it.
Yeah. And then we would have the log base 10 of 5. So log base 10 of 5 plus 3 log base 10 of x plus log base 10 of y. So that's expanding it or writing it as a sum in this case of multiple logarithms. So if we look at letter B, we have the natural log, same thing. It just has a base of e instead of base of 10. We have the square root of 3x minus 5. That's all under the radical, and then divided by 7. So Evan, what do you think we would do here if it's division?
Probably square the top.
So before that, how could we, so if you have division, that's property number 2. How would you rewrite it to get it out of the division format? So if it's division, how could I separate it into its own separate logarithms or natural logs? What would it become?
Sorry, I have no clue.
Okay. Somebody want to help him out? Jeremy.
Would it be ln?
Oh, Grant, go for it.
Would it be ln square root 3x minus 5 minus ln 7?
Yeah. So we're not doing anything with that square root right now. We're just taking the numerator, making it its own log, and that's based off of the second property. So it says if you're dividing, you can separate it into the log of the value on the top minus the log of the value on the bottom. Notice you have to keep the base the same. Well, this base is a natural log and it has an e. We don't have to write that in there. All right, we're going to continue to simplify this. We have a square root right here. A square root can be written as an exponent. Jack, do you remember, excuse me, if you have a square root, what is that exponent if it's a square root?
1/2.
Excellent. So because a square root can be written as an exponent of 1/2, we're going to change that square root to be the power of 1/2. And then Jack, what would you do with that power of 1/2? Jack, where would you move that exponent? Somebody help him out. What do we do with that exponent of 1/2?
You'd move it in front.
Yeah, we just move it in front. So the exponent gets moved in front, and we have 1/2 ln. Keep 3x minus 5 grouped together in parentheses, because all of that is contained with that ln, the natural log, and then minus ln 7. This doesn't get separated. So I don't separate that any further because it's in parentheses grouped together. Those are grouping symbols. It holds those two terms together. So I would have 1/2 ln and then the quantity 3x minus 5 minus the natural log of 7. And that would be my final expanded answer. Does anybody have questions on those two problems? So expanding means separating it into, in this case, 2 different logarithms. And the reason it's 2 is because I have something on the top, one quantity on the top, and I have the number 7 on the bottom. So division gets separated into subtraction. So the last 2 problems on here want you to condense. So it's like the opposite of the problems above. It is an expanded form. Now we're going to do the opposite and try and squish them together. So pull these examples or pull these expressions back together. See if you can try and figure out what to do with letter A. So there's a 1/2 log base 10 of x. You're adding that to 3 log base 10 of x plus 1. Again, think of those 3 properties. This one has addition. We have numbers in front, that coefficient in front of each of them. Parker, do you have an idea of what we should do with that coefficient in front of each separate log?
I'm drawing a blank.
So if you look at your property above, this n here, if you go on the other side, where can that n go? Kaden, can you help them out? What would we do with that constant or the coefficient in front of the natural log?
You would
Or
make it the exponent of x.
Yeah, so it becomes the exponent. So these properties, you can go back and forth with the property. So I could have the right side and I can move backwards to the left side. So if it's in front as a coefficient, it moves back next to the variable as an exponent. So again, they can kind of go back and forth, these properties. Equals means I can kind of move from one to the other side. That's what equivalency means. So I'm allowed to use either side and kind of go back and forth between the two. So this would become the log base 10 x to the 1/2. Kaden, how about the next expression?
It would be log base 10 x cubed plus 1.
Actually, we're going to keep it in parentheses because it is in parentheses. So it would be x plus 1
to cubed.
to the cube, right, or to the 3rd power. So the quantity has grouping symbols. That 3 goes on the outside of the grouping symbols. All right, we're going to continue to simplify. If you have a 1/2 exponent, this 1/2 exponent can be written as the square root of x. A quantity that's in factored form is considered simplified form. So I wouldn't want to do anything with that x plus 1 cubed. So I wouldn't want to try and FOIL that and expand it because it's already in its simplified form. And then the last thing, I still need to condense these together. Gianna, what would we do to condense these together so that we have 1 log instead of 2 logs? Jenny, do you know what we would do to condense these together? So if I have addition, how can I pull them together?
Sorry. You would have them both be log base 10, and then it would be the square root of x times the quantity of x plus 1 cubed.
Yep, perfect. That's it. So addition from above can become multiplication. Again, if I have addition, I can condense them to be multiplication. So those properties can go either way. Addition condenses to be multiplication. So my goal was to get it to be one logarithm, and now we have one logarithm. So let's see if we can quickly do this last one. I know I see it, the clock changed to 9:33. So the first thing, I would take that 2 and make it the exponent of that quantity. Again, keep it a quantity. If it's in parentheses, it remains in parentheses. And then to condense it to a single log, subtraction goes with division. So I keep one natural log in front, and then we have x plus 2 squared divided by x. Notice I don't have a natural log divided by a natural log. We're condensing the expression or the pieces after the log into division by its property. So this here is my final simplified answer, condensing it to one log. Anybody have questions? So I pulled up some of the homework just so that you could see, like, you're going to be condensing the problems. I gave you the odds of a couple different groups of problems. So you're going to be condensing them together, or you might be expanding them. But you're going to try and use those properties to condense or expand depending on what the directions are asking you to do. So have a great day. I'll see you all tomorrow. If you have questions, remain on. See you later.
Thank you. Have a good day.
Bye, Miss Kane.
Have a good day.
Miss Kane, what was the answer to A again? I missed it.
Yep, the one we just did?
Yeah.
Yeah, so the log base 10, and then the square root of x times the quantity x plus 1 cubed.
Okay, thank you.
You're welcome.
Have a good day.
Thanks, you too, Hannah. Olivia, do you have a question? Ooh, didn't mean to do that.
Nope, I'm all good. Thank you.
Okay, yep, we'll see you later, Olivia. Have a good one.
See ya, you too.
Thanks.